Hi, Bobby.
Hi, Anirudhan. So we were discussing about Thevenin equivalent circuit.
Yes.
Maybe we'll draw and then,
Okay.
because it seems this it may get more understanding. I mean, it may help to give more understanding about the circuit.
Sure. So tell me what to draw and I'll draw it. you are going to drive
just
the
Thevenin
network.
equivalent circuit.
Okay. Thevenin equivalent.
Connect
So I think our Thevenin.
VTH.
Okay. So VTH and RTH.
RTH. And then a load resistance.
Oh, and then a load resistance.
Yeah.
Okay, that's quite simple. I'll call that RL.
Yeah.
Okay.
See, actually, this circuit is driving the load RL.
Correct. So our yes, correct. So if I imagine this, something to the left of this, we have replaced by the Thevenin equivalent.
Yes.
Correct. You are right.
And if I am that RL, I would like to grab as much as from the source.
Okay, I understand. Yes.
So how can I get the maximum from the source?
Hmm.
Can you give some idea?
Okay. So you want to maximize the power delivered to RL.
Exactly.
Right?
Exactly.
Okay. Well, maybe we should just start, write the expression for RL.
Okay.
Shall we start with that?
That should be, yeah.
Okay.
Yeah.
So this is a relatively simple circuit. So maybe what I will do is the current through this mesh
We can
is
write
VTH by RTH plus RL.
Exactly.
So the current is VTH is the RMS value,
Yeah.
or in this case DC.
DC.
So my talking about AC has all has me wondering about RMS value.
Yeah.
But this is just DC, right?
Correct.
So no problem.
But if it's an AC circuit, it will be RMS.
It would be the RMS, right? Okay. So I would be VTH by RTH plus RL, right? And we want the power delivered to RL, right? So that is, I'll call that PL.
Okay.
That is just I squared
RL.
times RL, right?
Oh.
So it is VTH by RTH plus RL the whole square times RL.
Okay. So we just want to maximize this.
You want to maximize this. What is a good way to do it?
Anyway, RTH and VTH are fixed. I can only change RL.
You can only change RL, right? Okay. Oh, then the easy thing to be, take the derivative of PL with respect to RL. We'll set that to 0.
Sure.
Right? So let's do that. So I'm going to say dPL by dRL. I want it to be 0. Okay. So that is relatively easy. So that I need to take the derivative, right?
Yeah.
Okay, so if I take the first one, so RL times derivative of VTH by RTH plus RL the whole squared.
Yeah.
So that will be 2 times VTH by RTH plus RL. So I've just taken the derivative of this.
Yeah.
And then I have to take the derivative of what is inside.
Denominator, yeah.
Okay, so that would be VTH. I'll write it outside like this. I have to take the derivative of 1 by RTH by RL. So minus 1 by RTH plus RL the whole squared.
Okay.
Okay, so this is the derivative of the first function times RL. I have put it in the front.
Okay.
And now I have to take the derivative of the second one, that is just 1. So it is just the first term times 1, and I have to equate this to 0.
Okay.
Right? Okay, I see some
certain terms will get cancelled.
Certain terms get cancelled. Let me see. I see VTH times VTH and VTH squared.
Yeah.
Right? So I think this term should be no problem. And I see RTH plus RL the whole squared, right? So this, maybe I'll use a different color. So this and this.
Yeah.
All right. Okay. So maybe I'll take the first term to the right hand side.
Yeah.
And let's try to simplify. So 2RL by RTH plus RL will be 1. Right? Okay, maybe I'll just write it like this. Minus 2RL by RTH plus RL. That is the first term.
Yeah.
Plus 1
equal
to 0.
Correct.
Okay, so then I'll take this term to the right hand side. So 2RL is RTH plus RL.
Yes.
Oh, okay. So that means RL has to be RTH. Okay, that's interesting. So, this is interesting. So what this is saying is, if I set the load resistance value of RL to be equal to the Thevenin resistance, I will dissipate maximum power in the load, right? So technically, by the way, I just realized something. If we want to show that it's a maximum, we have to take the second derivative and check the sign, isn't it? But we will give that as a homework, right? I think students will understand that it is not a minimum, because the minimum will happen when RL is equal to 0 or RL equal to infinity. I think both of them will give you minimum, right? So there is either no resistance or no current. So this will be the maximum value for sure. But we will give that as a homework. They can take the second derivative, see what happens. We are interested in the result. So it looks like this is a very interesting result. If the load resistance is equal to the Thevenin resistance, it gives you maximum power
transferred to
the load. Yes.
Hey, this is very interesting actually.
Yes. I think it has a name.
Maximum power transfer theorem.
Maximum power transfer theorem. That's right. So this is the maximum power transfer theorem. That's right.
Curiosity. Is this also valid for AC circuits?
Let's find out. But actually, I just realized we don't even know if Thevenin equivalent exists for an AC circuit. We should look at that first.
That's true.
Right?
Yeah.
Shall we look at that
because
first?
We have been discussing only DC circuits.
Only DC circuits. So let us maybe quickly define Thevenin. And it so happens that it is valid. Let us quickly define, right?
Okay.
So now our definition, I think we started off with some network, no?
Yeah.
We said the network can have voltage, current sources, voltage sources, and I think here we can have AC current sources, AC voltage sources, and resistors. We'll start with this most basic definition.
Yeah.
Right? Then you can have a Thevenin equivalent across two nodes, A and B. We can say that there will be a single pair of VTH and RTH.
Okay.
This is the most basic form of the AC, right? And you also have a Norton equivalent.
Yeah.
Right? So we can also say that there is a Norton equivalent, which will be an AC current source in parallel with a resistance.
Yeah.
So across the same set of nodes A and B.
Correct.
So this is IN and RN. This
RN is RTH.
RN is RTH. So maybe I'll just call it RTH here. And actually, I think we should extend it to inductors and capacitors. Because we know that they matter for AC.
Correct.
So what I will do, I will just show this color. So if I have some inductor and capacitor, then what happens? Well, if you only have inductors, for example, most likely there will be some inductive impedance.
Yeah.
And if you have capacitors, more likely there will be some capacitive impedance. So if that is the case, then we'll say that the Thevenin equivalent, well, the Thevenin voltage will not change because you are looking at the open circuit voltage across A and B.
So RMS value of that voltage
will still exist, right? There will be some voltage. So we again, at least the definition of Thevenin voltage value itself may change.
Correct.
Right? That if you suddenly have an inductor somewhere, the Thevenin voltage will change.
Yeah.
Right? But the definition of Thevenin voltage as the open circuit voltage will still be valid.
Yeah.
Right? So we will say V Thevenin. In series with now, it will have R and L and C.
So some impedance.
Some impedance, right? So we'll just call it some impedance like this. As always, we'll just say across A and B.
Z,
correct. We'll just call it Z Thevenin.
Okay.
And again, we can have the Norton equivalent of that as well. So you'll have IN in parallel with RTH or Rn across A and B. So interestingly enough, the minute you have inductors and capacitors, it does not mean this VThevenin and the old VThevenin need not be the same. The magnitude may be different, even angle may be different, right? So we need to...
Because that was anyway DC.
That was anyway DC, right? No problem. And here again, VThevenin IN, ZThevenin here. Because ZThevenin is a complex number, R plus JX, VThevenin and IN will have an angle relationship, a magnitude relationship and a phase relationship, right? So I'll just write that down here. So IN will basically...
so all these can be complex numbers.
Yes, exactly. That's what we are trying to say, right? Maybe I'll just write it in complex form like this, right? That's what we are saying.
Yeah.
Okay, great. So I think now this is basically Thevenin's theorem for AC. It is just a straightforward extension of what we did for DC. For DC, we said it is just VThevenin, RThevenin. Now we are saying it is VThevenin, ZThevenin, where both are complex numbers.
So this ZThevenin can be some R plus JX.
R plus JX, correct. So
or RTH plus JXTH or whatever.
Okay, maybe we'll just do that. Yes, RTH plus some JXTH, correct. It will have a real part and an imaginary part.
Oh. Now do you want to go back to maximum power?
Yes, I think that is your original question, right?
Yeah.
So that we'll go back to that maximum power. Oh, okay. So let's do that. I think R plus JX, right?
Yeah.
So VTH and RThevenin plus JXThevenin.
Yeah.
But now the load was RL here.
Yeah.
Should I use the same RL or should I use...
We'll put some reactive load.
Reactive load.
Yeah.
Okay. So load also, maybe we don't know if it has an imaginary part.
Yeah.
So RL plus JXL?
Yes.
So XL is not inductive.
Or JX. Oh, because it's L.
Yeah.
Sure, load. Yeah.
Load.
Let it
but they should not confuse it with inductive reactance.
Yeah.
That's all.
Yeah.
Right?
Understood.
So RL plus JXL.
Yeah.
And now...
same procedure we can follow.
Same procedure, but what did you want to find out again?
Maximum active power transferred to the
okay.
load.
So now that it's complex, now you are making it finer, right?
Correct.
You're adding more information. So
Yeah.
maximum active power transferred.
Yes.
So I am looking for power, not the reactive power.
Not the Q or
not the
S.
Q. Correct.
P alone.
Only P alone,
Yeah.
right? So you're interested in P alone. So you're interested in this.
Yes.
Okay. Real part of V I star.
Yeah.
Correct?
Yeah.
Okay.
Yeah.
Perfect.
Yeah.
If you're interested in that, then P, so I'll just write it here. P, suppose there was a current I and now it's a complex number, right?
Yeah.
It should just be, I should be able to find out because that current is flowing through RL.
Yeah.
I should just be able to find out the square of this and multiply it with RL.
Yes.
Right? But I is a complex number.
Yeah.
So I just need to be careful. And these are all RMS values.
Yeah.
Right? So I need to do this, something like this.
Or current, we can take the magnitude also.
Magnitude also,
Yeah.
directly, correct? So this is just the magnitude of the current times RL.
Yeah.
So current magnitude is VTH by root of RTH plus RL the whole squared.
Yeah.
Plus
XTH plus
XTH plus XL the whole square. Right. Okay. So this is the current magnitude.
Yeah.
And I need to take the square, right?
Yeah.
And multiply it with RL.
RL.
So this is P basically, or PL if you want to call
Correct.
it, right? So if you had done this is your new power.
Yes.
Okay.
So here I can vary RL or XL.
Correct.
That's what I can vary.
That's right. So you need to find out what is the RL that will give you maximum power dissipated in RL. What is the XL that will give you maximum power dissipated in RL?
Yeah.
Right. Okay. So let's first simplify this. So this PL is VTH squared by, this would be RTH plus RL the whole square,
Yeah.
plus XTH plus XL the whole square
Into RL.
into RL. Okay. So we need to do both, no? Okay, let's go back and see what we did here. So we wanted to find out RL for the DC case.
Derivative with respect to RL.
But now we have to take derivative with RL and with XL.
We'll do with XL first.
We'll do with XL first. I think you're right. Let's do derivative. So we have two things, no?
Yeah.
So dou PL, now partial derivative.
Yeah.
Right? I'll use the, okay. So dou PL by dou XL is equal to 0.
Yeah.
And we also need to do both. Right?
Yeah.
We'll do this first.
We'll try with one first. Yeah.
First one.
Yeah.
Okay. So we'll do dou PL by dou XL equal to 0 first.
Yeah.
Okay. VTH is not a function, RL is not a function. So VTH squared times RL. So I have some one, so my in times minus 1 by denominator whole squared again. So it will be RTH plus RL the whole squared plus XTH plus XL the whole squared, whole thing squared, right? So it will be minus, it's like a 1 over something function, minus 1 over the denominator squared times now the derivative of the denominator. And derivative of the denominator, RTH plus RL the whole squared is not a function of XL.
Correct.
So that will go away, that will just become 0.
Yeah.
So 2 times XTH plus XL.
Yeah.
Oh, sorry. 2 times XL, and that's it. I've already taken VTH squared times RL.
Correct.
Here. Okay.
And
this should just be 0. Okay.
Anyway, RL cannot be 0.
RL cannot be 0. VTH squared is not 0.
Yeah. So
I think it's okay. So this is working out very simple actually, right? So XL should be minus XTH.
Yeah.
Right. That's what this is saying. So if you want maximum power transferred to RL, the load, reactive part of the load should be said to be negative.
Or
yes. So what this means is if the load, if the Thevenin equivalent impedance ZTH was inductive, you want the load to be capacitive.
Okay.
Okay. And if the Thevenin equivalent was capacitive, you want the load to be inductive.
Oh. So that means the overall reactance of
in the loop should be 0. That's what it is saying, right?
Okay.
So the overall, correct, that's right. In fact, now the current is becoming much simpler, no? If XTH plus XL is equal to 0, XL is minus XTH, XTH plus XL is 0.
Then it has come back to our previous
case, right? So then automatically PL just becomes only the resistive part alone.
Yeah.
That is just VTH squared by, okay, so this is just
we don't need to do because we have done earlier.
Yeah. I'll just write down the expression here, RTH plus RL the whole squared times RL.
Yeah.
And this is exactly the same as I think what we did here.
Correct.
And we saw that RL is RTH.
Okay.
We get the same answer. So dou PL by dou RL equal to 0 will give us RL equals RTH. Okay, that's interesting. So let us write this down. RL is equal to RTH, XL is minus XTH. Okay.
So basically it is a complex conjugate
of the Thevenin impedance. That's true. So that is what we need, looks like.
Cool.
Interesting. So AC maximum power transfer.
So the reactive power should get cancelled and then resistive powers will be equal.
That's right. So the reactive powers should cancel out and the resistive part should be equal.
So when I take maximum, half of that is lost inside the network.
Actually, you are right. So in fact, that we should have noticed right here, right?
Yeah.
The minute RL is equal to RTH, even in the DC case, if you are delivering a certain amount of power in the RL, the same amount of power will be dissipated in RTH as well,
Yeah.
because the same current is flowing through both of them.
Correct.
In fact, so that means efficiency will be, it's almost like half,
Yeah,
no?
yeah.
You are burning as much power inside your
Correct.
Thevenin
Correct.
as you are burning in the load.
Correct.
Okay, that's
When
interesting.
maximum power is transferred.
When maximum power is being transferred. Correct.
So this is irrespective of value of the RTH.
That's right. This is irrespective of value
It
of
can
RTH.
be 1 milliohm.
It can be 1 milliohm or 1 mega ohm.
Correct.
Or 1 ohm.
Yeah.
It doesn't matter.